Good afternoon, everyone. I, Shaditra Gangopadhyay of St. Xavier's College, Autonomous, Kolkata, thank each and every one of you for being here with us today for the webinar organized by the Department of Mathematics, St. Xavier's College, Kolkata. We aim for the exchange of information and ideas relating to the beautiful subject that mathematics is. We all understand the importance of science and technology and innovation in our day-to-day lives and the ways in which they are transforming the world. If this was not clear earlier, it is blindingly obvious now in the time of the COVID-19 pandemic. Science, technology, and innovation are indispensable for our response to and recovery from this crisis. Mathematics is a science binding all the other sciences together, thereby forging what mathematicians would call an order to the chaos. Gracing the occasion today, we have Reverend Father Dr. Dominic Xavier, Principal, St. Xavier's College Autonomous, Kolkata. I would like to elaborate on the rich legacy that he has created for himself over the years. Father has been a professor of economics at St. Xavier's College, Kolkata, Vice Principal of Commerce and BBA. He is also the President of St. Xavier's College Alumni Association. Reverend Father Dr. Dominic Xavier is a recipient of the prestigious Maulana Abul Kalam Azad Award for his contribution to higher education, as well as the Award for Excellence in Education and Philanthropy by the Bengal National Chamber of Commerce and Industry. In such an unprecedented situation, Father has been leading the college from the front, and his leadership has been a source of motivation for all of us. On behalf of the head of the department and the entire faculty and students of the Department of Mathematics, I now welcome our principal, Reverend Father Dr. Dominic Xavier, to inaugurate this webinar with his welcome address. Dear Father, kindly initiate and preside over this webinar.
So very good evening to all of you. I extend a warm welcome to all the participants of this webinar and Sandpile, Odometers, Membrane, and Random Forest, organized by the Department of Mathematics, St. Xavier's College, Autonomous, Kolkata. I would especially like to welcome the speaker for today's webinar, our former student, Dr. Rajat Subhra Hazra. In a very special way, I would like to welcome all our respected faculty members and our students and the head of the department. I welcome them and also thank them for organizing this important webinar. I know that students and professors are busy with exams and online classes, but still you had time to organize this very important webinar by the very important person. Data science provides a plethora of classification algorithms such as logistic regression, support vector machine, and decision trees. But near the top of the classifier hierarchy is the random forest classifier. With the rise in computational algorithms, the intellectual discussions on random forests will definitely stimulate our thinking in the research orientations. The topic of this webinar is in tune with this thinking process. Having said that, the reputation of the college is built largely through the accomplishment of its alumni. The glorious alumni of this institution have continued to contribute to the nation, which is brought honor to us on several occasions. Not only do we enjoy the glorious achievements and success of our alumni, but also take pride when we see them paying tribute to the underlying philosophy of Nihil Ultra, echoing the ethos of the institution to serve humanity. One such a very bright, young, enthusiastic alumnus of the college has provided us with the ample reasons to smile in this trying time when he has been selected for the prestigious Shanti Bhatnagar Award. This young mathematician is Dr. Rajat Subhra, an associate professor of the Indian Statistical Institute, Kolkata, and a 2003 graduate of Mathematics Department of this college. I take immense pleasure in welcoming Dr. Hazra once again and congratulate him for winning this very prestigious science award for notable and outstanding research work in mathematical science. I'm sure all of us, we can put our hands together and show our appreciation to Dr. Hazra. Yes, sir. I'm sure this evening going to be a very, very stimulating, kind of listening to Dr. Hazra, who has done a lot of studies, and surely we are very, very happy to have him. We are very proud of him. I'm sure that when the new normal, everything is over, when we have the offline classes, when we are able to meet in person, surely we will invite Dr. Rajat Hazra, and surely we will felicitate him for this real achievement. Having said that, finally, I would like to thank the Department of Mathematics for organizing this webinar. I wish this webinar a success. And especially, I would like to thank Dr. Sucharita. You said as soon as the award was announced, Father, Dr. Rajat Subhra Hazra, our student, and he happens to be her classmate. I think that's what she told me. I said, you go ahead, you must do something to organize a webinar, anything, and she has done. So thank you very much for the beautiful arrangement and inviting Dr. Rajat Subhra Hazra. Thank you very much. Have a wonderful evening. Wish you all the best. May God bless you.
Thank you, Father. So, without further ado, let me introduce the head of the Department of Mathematics, St. Xavier's College, Autonomous Kolkata, Professor Sucharita Roy. Ma'am will introduce everyone to today's speaker, Dr. Rajat Subhra Hazra.
Reverend Father Dr. Xavier, Principal, St. Xavier's College, Professor Bertram De Silva, Vice Principal, Arts and Science, Dr. Tapoti Doctor, Dean of Science, Dr. Orgho Banerjee, Dean of Arts, Dr. Royan Chandra, Member Secretary, Academic Council, Dr. Parthapratim Ghosh, IQAC Coordinator, esteemed faculty members, and my dear students. I, on behalf of the Department of Mathematics of St. Xavier's College, Kolkata, welcome you all once again to this departmental webinar. I take great pleasure to introduce Dr. Rajat Subhra Hazra, the speaker for today's webinar. It's really an honor and privilege for us to have him today. I would like to take this opportunity to personally thank him for accepting our invitation without giving a single thought in spite of his extremely busy schedule. Dr. Hazra is presently an associate professor in the Indian Statistical Institute and a fellow of the Indian Academy of Sciences. His research interest lies primarily in different domains of probability. This year, Dr. Hazra has been awarded the Shanti Swarup Bhatnagar Award in Mathematical Sciences. He also won the Young Scientist Award by the International Indian Statistical Association in the theory section. He had received the INSA Young Scientist Award in Mathematics in 2016 and also received the prestigious Inspire Faculty Fellow in 2014. Rajat was my classmate in undergraduate studies at St. Xavier's, Kolkata in the Department of Mathematics. Then he did his master's from University of Calcutta, Department of Pure Mathematics. He had completed his doctoral research from ISI Kolkata in the area of probability and remained deeply dedicated to academic research as he went on pursuing his postdoctoral research work in the University of Zurich from 2011 to 2014. Today, we are fortunate enough to have him with us for delivering a talk on the topic Sandpile, Odometers, Membrane and Random Forest. So, I once again welcome Rajat to this webinar. Before I hand over the session to him, I'd like to announce that we will be taking the questions once the lecture is over. I request all of you to type your questions either in the Zoom or in the YouTube chat box. So without any further ado, I hand over the session to Dr. Hazra. Over to you, Rajat.
Thanks. Thanks a lot. There is no chance of a second thought when Xavier invites me, because it's a very special place. Firstly, I would like to thank Father for his very humbling words. I don't know, like it feels really, I'm touched by his words. It means a lot to me. And just to tell you a few words before I start sharing slides and go to the technical part. When I left home, my house is in Asansol. And when I left home, I came to St. Xavier's in 2000. I got admission in the hostel. Father Anil Gomes was our warden, and he welcomed us very well. And I can tell you, I have been out of my house for 20 years. And those 3 years in St. Xavier's hostel was the best home I had after I left home. And and it's true for all of my friends who were there. Like we still cherish that, and those were very special. I would also like to thank, because it's an opportunity to thank people, I would like to thank my teachers in St. Xavier's, who were a great inspiration in making me love mathematics. Especially, I would like to thank two people who are not in the department at the moment, are Parthopatim Ghosh and Professor Anando Dasgupta from the physics department. They used to take a special care for few of us in the evenings and teach us lots of nice mathematics. And it was fantastic. And those evenings were one of the best days I had during the college. And they gave tremendous inspiration. And I'm hoping that even today's teachers would take special care for students who are eager to learn more and do research, and spend some extra time on them. And that really helps. I don't know, many of you the students who are listening might not know that Father Gore was associated with St. Xavier's College. He was one of the last pupils of Albert Einstein. Albert Einstein didn't have a PhD, but he taught people. And Father Gore was one of his students. And he was the initiator of the math department. And we had a nice center called Father Gore's Center, where we used to discuss a lot. And I would encourage everyone to again bring back those charms or the ideas of Father Gore again to the department, and again make it a big unit. And I'm sure now St. Xavier's is becoming an university, and it will is an university now, and the research will be top class from the university. Okay, so this is the thank you part, and now I'll start sharing the slides. I'll go to the technical part, and I thank everyone for the Sushurita also for the nice introduction. She's my classmate, and whenever she calls me, I'm there. So it's a nice pleasure. So can I share the slide now? Maybe I can share it. So I hope this is visible. Can anyone just let me know if this is visible or not?
Sir, it's visible, sir.
Okay, so I'll go full screen now. Okay, so let me go to the talk now. My talk has, as you can see, it has 4 names in it: Sandpile, Odometer, Membrane, Random Forest. While I was making the talk, I had to skip one part. I'll indicate where these things arise is the random forest, but it was becoming a long talk, and I understand it's a Saturday evening. All of us had online classes and everything. Maybe it's tiring. So I wanted to, I'll just indicate the first 3 things. So my talk has, you can think of it as kind of a season 1 of web series. It has 4 episodes. You'll see what are the episodes are. Episode 1, 2, and 3, and 4. And gradually, what will be the link with the episodes? It will be clear slowly as the talk progresses. So let me start with episode 1. It's called the biharmonic or the bi-Laplacian operator membranes. Once upon a time in a kingdom far, far away. Okay. So I'm not going to tell you a fairy story here. It's not a fairy tale, it's a mathematical lecture. But why I started with this thing from a fairy tale? Because in my talk, I'll be not mathematically precise. And when you see fairy tales, there are different kind of things which are unreliable. So you have to take things with a pinch of salt when I'm saying the mathematical parts, because I'll try to make it accessible to different parts of different areas in which people belong. So maybe you are from computer science or from physics. So let's start with the story. It's a fantastic story. Once I read it, and I wished I had the opportunity to share this story. So it started in a really long time ago, in 1987 by a physicist and musician who studied law also. So he was Chladni. Chladni made as you can see, it's a picture of Chladni here, and he made a very, very interesting experiment. So what he did was, you can see a plate here. So this is called a vibrating plate experiment. He took a plate, he took a bow of the violin and struck on the boundaries of this plate. And then he sprinkled some sands on it, and he could see some patterns appearing on the vibration of this plate. One thing to note, this plate was fixed in the middle, and there were boundaries which were free. So this is not the first time. In 1987 he did the experiment. Interestingly, this appears also in Leonardo da Vinci's notebook, and also Gauss wrote some articles where he observed this kind of things. But proper experiment was done by Chladni, and what he did was he did these experiments one by one. So what he was doing is he touched his bow at different places, and it would make a different kind of sound, and he would see different kind of patterns appearing, and he noted them down. He drew them. So what he did was he noticed that when he tried to excite a metal plate with the bow of his violin, he could make sounds of different pitch depending on where he touched the plate with the bow. The plate itself was fixed only in the center, and when there was some dust or sand on the plate, for each pitch, a beautiful pattern appeared. So this is the original drawings by Chladni. You can see different kind of patterns, beautiful fractal patterns, quite symmetric in nature, appearing. So what Chladni did was he went around different places. So he was from England, and he went around from different places doing this experiment and challenging mathematicians to explain this. So there were not really mathematicians during that time. Everyone was a philosopher. So he was challenging those philosophers to explain the philosophy behind this thing. So incidentally, what happened, he was once invited at a dinner by Lagrange to Napoleon. So Lagrange was sort of, during that time, associated with the Academy of Paris. And so he invited Chladni to do the experiments. Napoleon was extremely fascinated. He said, I'm going to announce a huge prize. It was almost during that time 3,000 francs, which was quite a big amount. And he called it the prize extraordinary. And he said, anybody who comes with a mathematical explanation of what is happening will get the prize. So there were initially 2 contestants for that. So there were some molecular biologists who wanted to explain it through some things, but that failed. So Denis Poisson, we know of Poisson integrals, Poisson process. He was a big mathematician during that time. He wanted to be a part of that competition, but Napoleon requested Poisson to be the judge of this contestant. But when it was time for the entries to come, actually there was only one entry. And this entry was by Sophie German. So, and Sophie German was the only entry, and what happened was there was a flaw in the double integrals she computed, and her approach was correct, but there was a mathematical flaw and it was rejected. Next time, the competition again opened, and she submitted it again. And then in the final attempt, there was again a flaw. And in the final third attempt, she got the problem and she was awarded this prize. So in between, after the second attempt, there were some mathematicians like Kirchhoff and other Lagrange himself who helped her to get it during that time. But one of the fascinating things about Sophie German is, so here is a picture of Sophie German. I'll come to that. She was one of the, as you can see, she was a female mathematician. And during those days, it was so difficult for women to enter the area of mathematics. Even in Academy of Paris, women were not allowed to come to a physical class. So what he did, she had a very good friend, Monsieur Leblanc, and she got the notes from Monsieur Leblanc, and in fact, she took her name and used to write to Lagrange. And Lagrange was very impressed by the letters, and Lagrange asked that we should meet sometime, in fact. And when she met Lagrange, Lagrange came to know that she was a lady, and that's how it happened. Another interesting story I want to tell about Sophie German is Sophie German, after she became famous, but she was not known. She was still treated like a foreigner. So what happened? She started communicating with Gauss on a special case of Fermat's last theorem. She was one of the first, she made the attempt to solve the Fermat's last theorem. And she wrote to Gauss. Gauss initially didn't reply, but during that time, the French had a war with the Germans, and Gauss was in Braunschweig during that time. And Sophie German came from a very well-known family. She knew a colonel. She told him that they should take care of Gauss and no harm should be done. And the colonel went there and told about Sophie German. But Gauss was surprised that he doesn't know about any Sophie German. And soon later, he came to know who Monsieur Leblanc was, and she was the one. And they started collaborating through letters. So it's a fascinating life of one of the most struggling women during that time. And she produced brilliant mathematics. She was not well trained, but she had quite an inspiring amount of mathematics during that time. And so, and the predictions were really fantastic in the sense, she said that Chladni's figures are zero set of a function. So if you take a function, if you look at the points, so in the, it's a function, and if you look at the zero sets, those zero sets are those curves. She said that. Okay, and so what was happening is, so you can, when you vibrate the plate, you will see that there are jumping, so the plates has a small amount of jumping in it, and there are places which are like, so this is the figure to show you. So when the plate vibrates, this is the magnified thing. You can see here that there are places which are bouncy and jumping. So you can see a mountain landscape here. And what is happening is the sand is also jumping, and it's settling on these nodal lines, what we call the function, places where the function is zero. And what is this function which has this hill-like structure is, you can see here, it's a function which satisfies this differential equation. So it's called delta square G, which is given by, okay, I'm not going into the expression here, but it's an equation given by delta square G equal to lambda G, where delta square G is this equation which has a fourth power. You can see it's those are are known with the technicalities. It's a fourth order differential equation, differential operator acting on G. Now, one way, I think those who are student of mathematics or science, nowadays it's in school also. If you think that delta squared, this is a matrix, then delta squared G is equal to lambda G is nothing but an equation. It's an eigenvalue equation. So lambda is an eigenvalue and G is an eigenfunction if G is non-zero throughout. So what happens is you can extend this matrix theory to a level of an operator theory. I'll come to that later. It's the one of the key mysteries which will come later, that these G's are eigenfunctions of this operator delta square. And what you see is the zero set of this eigenfunction. I'm not going into the physics of how the equations were derived. It's not very difficult. It comes from simple wave equations which are there, and one can go through it. And just to point out those who are listening here, just keep this picture in mind. I'll go to a completely unrelated story and come to this picture in the end. So keep this picture in mind. It's a very important picture to keep in mind. So just to tell you that although Sophie German gave a solution, there were still the final solution had some mistakes in it. Now, the mistakes were not very critical, but on this mathematical sense, it was very critical in the sense that she forgot some boundary conditions. So first, this was noticed by Kirchhoff, who was helping German, by the way. And Kirchhoff, who is also known for his works in electrical networks, and I'll come to that. He's also known for spanning trees and forests. So Kirchhoff is related to many things. Kirchhoff kind of tried to solve this. Finally, it was Ritz, whom we know about the Rayleigh-Ritz quotient, Galerkin-Ritz method, who solved it. He gave a perfect mathematical solution in 1909. So just to tell you, like this moral of the story I'm going to take from here is this operator, which is, I'll call it the bi-Laplacian, because this delta in mathematics is called the Laplacian, and delta 2 is called the bi-Laplacian. Laplacian in mathematics is a very, very important operator. Bi-Laplacian, not many people know why it is important. There is another fascinating story. I'm just going to tell you some stories. So this is another story which is related to bi-Laplacian. It's one of my favorite stories to share. One of the biggest architectural achievements was the Tacoma Bridge, which is a suspension bridge. It's a fourth suspension bridge which was opened. And just after 4 months it was opened, on November 7, 1940, it collapsed. Now, it was called the Galloping Gertie because, as you can see, this picture is not a fake one. You can see there is a car tilting, and really the bridge used to sway like this. And finally, on November 7, 1940, mind it, there was no storm, there was nothing. It was a wind speed of 40 miles per hour or something like that, which made this collapse. Now, people were confused on whether it's sort of with the natural frequency or which matched, or what kind of things happened here. So later, this is a very nice from a very nice article in the Siam Review by Gander and Kwok. They write, let me read you that. If we are interested in approximating the shape of vibrating bridge span, a simplified model would be to treat it as a thin vibrating plate, just like the plate which was used by Cladby, and consider the eigenmodes of the biharmonic operator acting on it. So these vibrations were sort of coming again from the biharmonic operator there. This model clearly ignores it's a simplified model. This model clearly ignores many structural features of the suspension bridge. In particular, it cannot explain how the bridge was initially excited. And while many physics textbooks treat this as a classical example of forced resonance, this explanation was shown to be incorrect in the American Journal of Physics by Bila and Scanlon. And those who study architecture, actually, this comes in one of the initial literature where they are taught about this faults with the bridge and what happened. It's a simple thing. Those who are hearing my lecture today, I would request you to go to YouTube today and look for the Tacoma Bridge collapse. And it's an unfortunate incident, although nobody was killed because they cleared the bridge before that. But it's recorded live how the bridge fell, and it's fascinating the vibrations which were occurring in the bridge. I'm not going into the technical details of how this, what are the mathematical factors which came into this, but instead I'll go to the next story, which is completely different from the episode 1. Okay, so I'm coming to one of the key topics in this talk today after this introduction, which is called the Abelian Sandpile dilemmas. Now, this is a brilliant quote. It says that, how do we know that creation of the worlds are not determined by the falling grains of sand? Now, although when Victor Hugo wrote it, I don't think he knew sandpiles, but it's a sort of fascinating quote here. I'll come to that why. Because these three people are one of the proponents of the sandpiles and what is in physics called the self-organized criticality. And so these three physicists, you can see here, it's Back, Tang, and Weisenfeld. So this, so what happens is, so they said there is, when we see some kind of a phase transition, for example, when we see a water evaporating into a vapor, there are some huge external features which has to be raised above the critical point to get a phase transition. So for example, water evaporating into vapor, you would need some kind of a temperature or pressure to be maintained or crossing some critical level. Orbach was kind of one of the first physicists who said that, okay, there are some systems which have some initial interior local interactions so that you apply very minimal amount of force on it and it will spontaneously reach an equilibrium state or what is called a critical point. And such systems are called the self-organized criticality. And this was a major breakthrough. What does it mean? So it just means that you have a system, you just do minimally something like excite it in the beginning, and it starts off moving on itself and creating some kind of a local dynamics among the structure in it, and then it stabilizes in such a sense that you can see very important factors which are there, like which you observe in the equilibrium state. So one can observe those factors, these things. And the fascinating paper was published in PRL. It's called the Self-Organized Criticality and Explanation of 1/f noise. One can read that paper. It's quite a non-technical paper, but has tremendous thoughts in it. So it's a suggested reading for everyone. So where is this applicable? I'll just give that it's applicable in many places. For example, this is from a quantum magazine. It's a brilliant example, and it's a major area of research now, that these systems which have self-organized criticality, or SOC, which is called, can be observed in, for example, in brain functionality. What happens is our brains are very complex structure. So whenever, say, for example, some bad thing happens, the neurons get excited, and slowly, as the days progress or everything happens, it calms down. So there is sort of an electrical activity which is happening inside the brain, which is slowly calming down after sort of avalanche of thoughts or big impulses to a stable position. So this is what Back writes: the electrical activity of brain cells shift back and forth between calm periods and avalanches. Avalanches are sort of, there is a huge, you think of, there is a huge change in the electrical impulse of the system, and then there is a low period, and then there is again an avalanche, then is a minor low period, and slowly it calms down. You think of the waves of a sea. Sort of when you see big wave on the sea, you will see the waves are slowly kind of dissipating. So you can see that, and the brain is always precariously right at the critical point. So it reaches the critical point, and this is a classic example of self-organized criticality. Now this is a theory which was proposed by Back, but there are lots of, I have met even few neuroscientists who are working on this, and I'm sure that this will be one of the breakthroughs in brain studies. But the mathematical aspect was actually started by a physicist in TIFR, extremely brilliant physicist Deepak Dhar, who is now in Pune after retiring from TIFR, was to study a sandpile model. So he discovered what is a sandpile. Sandpile is sort of, you can see this picture. This is a sandpile. So it's a piles of sand. What happens is you see a pile here. If you put in too much grain there, say at one spot, it will slowly start falling, and it will organize itself in another sort of sand dune. So what Dhar studied was, I'll come to why is it called abelian, sort of sand piles like this, and he called this abelian sand pile because of there is an abelian nature in it. And so what he did was with another physicist Satya Majumdar also. So they studied quite a bit of this, and they were, I can tell you, they were one of the fascinating mathematical papers I have read in my short span as a research career. They're just brilliant papers. So they initially studied in what is called Bethe lattice or integer lattice. Here is an example of a Bethe lattice. You can see that every point has 3 equal neighbors. So this is sort of a three regular tree. You can understand that every point has 3 neighbors. And this is what is called, this will be crucial in what I'm saying today, is called the integer lattice. So you think of a plane which is Z2, so integer cross integer, and each of these points are integer coordinates, and this is the grid which is called the integer lattice. So these are all integer points. Maybe somewhere here is the origin, then you have 0, 1, 1, 0, 1, 0, 0, 1, like this. So all are integer points. So this is the integer lattice. So they studied sandpile on this kind of structure. So what is, so let me show you what, or tell you what the sandpile is. So suppose I start with this. 1.2, before I go to the mathematics, you see, you take a point here, it will have 4 neighbors. What is a neighbor? Neighbor means I can directly jump to the point on these. So if you take one point here, it has 4 neighbors. So this is the point, and it has 4 neighbors on it. So let's start on Z2. You start with n particles in the origin. Say n may be 100, 1000 or anything. Any site has 4 neighbors, as I showed you. I give you a rule. What is the rule? Any site which has at least 4 particles is unstable, and it topples. It topples means it topples by sending 1 particle to each of its 4 neighbors. So I'll show you this game in a moment, and continue until all the sites have less than 4 particles. And now you can think that, okay, I am here, I have say 5 particles, I give 1 to here, 1 to here, 1 to here, and so on. Say, suppose this is 4. Now, suppose this is 4, this is 4, this is 4, this is 4. Which one do I choose? So Dhar's theory says that you can choose any one, any way. You can just do it it doesn't depend on the order. So he showed it through some operators, but that's the thing, that it doesn't depend on the order in which you topple. So that's why this abelian word comes into the picture. So the final configuration, when things are stable, if things are stable, I'll give you an example where things are not, when it doesn't reach stable, the final configuration will not depend on how you are talking. So this is an example which will make you understand what is happening. So I start with, say, a piece of this lattice. I'm not taking the whole lattice. I cannot take the whole lattice because it's an infinite thing. So let me start with 16 particles. Say this is the middle one. So this is the origin. And I have one. These are, say, I have one piece of grain there, one piece of grain here, one piece of grain here, one piece of grain. And here I have 12 pieces of grain. So what I do next is I give 1 to, so I am 12. I'm more than 4. So I'm unstable. So I'll give one particle to each of them. So I'm going to 2 now. So this is 2. Then I'm again giving particles to this. I'm still unstable because I'm 4. Now I am not unstable. I have given one particle each. But what is happening is I have 4 unstable particles now. So this is where the abelianness comes. You can choose any one of them. Say I choose this one. So what this does is gives one particle. So here is a neighbor. I haven't drawn it, but here is a neighbor. He gives it to what, this neighbor, this neighbor, this neighbor. And he himself, the 4 becomes, this 4 becomes 0. Let me choose this one. This, when you choose, he also has given 4 particles. This becomes 2, this becomes 1, this becomes 2. Now I choose this 4. Again, this 4 becomes like this. And finally, there is another one which is unstable. I choose that. Oh no, I have another one which is becoming 4. Finally, I have the stable configuration. Everything is less than 4. So this is a stable configuration. Now, let me show you. So this is another example created by Charles Smart, that you have, say, 24 things and you distribute now evenly 6 of them. Then you distribute more and finally come to a stable configuration, just like the one I showed. Now what you do is, for each of these 3 heights or 4 heights, 0, 1, 2, 3, you use different colors and you just plot these colors. Now, what about I started with 16 particles, or here 24? This picture looks like this. Suppose I start with 10 to the power 5 particles. Now you can see this picture arrives. So this is a toppling. This is the stable configuration, looks like this. Now you can see, just like Chladni, this is sort of a beautiful picture which has arisen from a sandpile toppling. Now the biggest question is, what does this figure represent? Is there a mathematical explanation for this figure? Or what can one say, what describes this figure? This is still a completely mysterious object, I would say. Not much is known about what kind of shapes these form. And what do I mean that this, as you can see, this is a background height 1. It means that initially I had started with all 1s on the place, on Z2. And then what I did was I added on the origin 10 to the power 5 particles. And then it had split up like that. Now, if the background heights are of the form 0, so initially all the heights are 0, and then you add a huge amount of particle on the origin, you can see this picture is formed. Say the background height is initially 1, and then you put again initially a big amount of sands on the center. So it organizes. So this is the self-organized part, that it organizes into shapes automatically. You don't have to do anything. There is no external force. It's the dynamics which you have started is playing the crucial role here, and it's kind of making this go on. So, and h is equal to 3. Why not h is equal to 2? And why not h is equal to 3? Just to give you a very, very interesting read, these pictures have some explanations through circle packings and obstacle problems. Those who are interested in the more mathematical nature can read this lovely paper by Lionel Levin, from whose webpage I have mainly taken these pictures. Lionel Levin is an expert in Sandpile. Lionel Levin, Peck, Gunn and Kwok. It came out in and also mathematics in 2017. Okay. Now, here are the So what happens? I didn't show you a picture for when the initial heights are 3. So let me give you an example what happened. Say all the initial heights are 3. Again, this is a part of Z2 where I had a chip here which is 4, and this is unstable. What it does is it gives 1 chips to here. Now all the 4 sites on the neighbors, they become unstable. Now they start distributing. So this becomes 5, this becomes 5, this becomes 5. So there are more unstable sites which are coming up. Now this is again the 5s you see are shifting outwards. The 5s become shifting outwards. And it's a simple game. You can start with this game and you will see that you can play it whole night, whole day, every whole your life, but it will not stop. So you won't come to a stable configuration. And this is what is called an explosion in the sandpile. So sandpile has a beautiful mathematical dichotomy here, that either you start with that sandpile, I explained you, either it will stabilize. What does stabilize mean? So every site will topple only finitely often. So at some point it will stop and you will see that beautiful picture. Or it will explode. It will keep on going like that. So every site, not just one site, every site will topple often, infinitely often. So let me explain you why you can say that, no, this is not the negative statement of this. So if I say the negation of this statement is every site will topple finitely often, would be that there is a site which will topple infinitely often. Now, so that's why I say it's a dichotomy here. Not these are not negative sentences. So let me give you a short, very easy explanation on why, if there is one site which will topple once, at least once, then it will topple infinitely often. So this is called a proof by contradiction. Those who are young here listening, so this is a proof by contradiction. So what I have assumed, so say suppose this is not true. Suppose a site which has toppled once topples only finitely many times and not infinitely many times. Suppose it doesn't. So there is a first site which has finished toppling. So it will stop toppling at some point. Now that, and call this the first. The first is important. The first site which has stopped toppling. You look at all its 4 neighbors. Since they are not first, maybe they may be second, they may be third, but they will topple at least once. And once they topple, they will give back some grains, in fact 4 grains, to that particle. Now that site which has stopped toppling will become unstable again, and it will have to topple. It will have to topple. So I hope this argument is clear, because this is one of the crucial basic argument in these kind of dichotomies. It's a 2-line thing, but it's a beautiful thing because of the dynamics. You see that the neighbors will, if a site topples once, it will keep on toppling, like keep on toppling like that. Now here I want to say a few things, like because I'm not saying any technicalities. Z2 is an infinite lattice. One might ask, you are doing something infinite here. That's why I said it's a fairy tale. So one has to be very careful about where this dynamics is happening, and one has to bound it by a box and let the box go to infinity. So there are many technicalities. There are beautiful lecture notes, beautifully, and also you can mail me if you want to know the details of that, but not in this talk. But I'm accepting that I'm hiding some of the mathematical parts. Now, as you saw, I had basic, I had these base heights, which was 0, 1, 2. Now, there are situations when the base height is actually, like in the brain, the base height is a white noise. What is a white noise? So this is the picture of a sound you hear, white noise. White noise has a precise mathematical explanation. I'll just try to describe what mathematically the white noise means. White noise means that you start with, say, Z2 or any graph you have. On each of these sites, you have what we call independent and identically distributed Gaussian random variables. So what roughly it means the initial sites are random. As you see in this picture, the initial sites will be like this. You don't know what are the precise heights. So you don't know here what are the precise heights are. So I have put in green here, independent, identically distributed Gaussian. Now, just to tell you what is a Gaussian. So S0x, x is a site. So it's a point on your graph. It may be a point on the integer lattice. So this is the initial random height. What does this mean that it is a Gaussian? It means that the chance that S0x, this variable, this is a random thing, this belongs to this interval, can be computed through this Gaussian bell-shaped density. So this is precisely the chance that S0x belongs to this interval is the area which is shaded here. So this is called the Gaussian density, and you compute the area which is there. So this gives you this curve is called the Gaussian density curve. And if such a thing happens that in your the chance that your initial random height belongs to this interval can be computed through Gaussian, you call it Gaussian. And independent means that this random heights do not interact with each other. So they are completely independent. So there are mathematical explanations, but you can think that a random height at point X and a random height at point Y is not related to any way. And identically distributed means all points can be computed through this Gaussian occurrence. So what is a sandpile? So I told you that dynamics is a sandpile, but sandpile is just a configuration. So it's a configuration where you have a vertex set, and on each of the vertex you have a sort of height. The Abelian sandpile, which I was saying to you, has this real line. This is the R, which is a real line, was a discrete set. So it was 0, 1, 2, 3, 4, 5 like that. Now I'm asking you a question about white noise. So it has a random height in it. So it can be a real value. Now, so what happens is for each of the X, what happens if the initial height is real value? So we have to change this process a bit. And this is called the divisible sandpile. And the rest of the 15-20 minutes I'll take in the talk will be about the divisible sandpile actually. So what happens? So here is the new rule of the game. Things are not discrete. So that 4 thing I have to change a bit. I say a vertex is unstable if my Sx, the height at the point X, is more than 1. Now remember, the heights can be negative also, because I'm allowing negative also. You can think of in the sandpile there are some holes which are happening. So that's how this can be happening. Now, what happens if the site is unstable? If the site is unstable, so it's more than 1, it keeps 1 to itself, and the remaining mass, which is Sx minus 1, it gives it to all its neighbors uniformly. I'm just repeating again. So a site is unstable if it has mass more than 1. So an unstable site topples in one way. What it does is it keeps 1 to itself, and the remaining Sx minus 1, he distributes uniformly to all its neighbors. So you can think that if there are 4 neighbors, say I am, for example, 25. So I'll take 25 minus 1, 24, and I'll distribute 6 each to my 4 neighbors. So this is what the divisible sandpile is here. Now, at each discrete time, you can all vertices topple simultaneously, or it can topple parallelly also. One by one it can topple. Again, there is an Abelianness here, that how you topple do not, the last configuration, last thing which comes, you see in the picture, it doesn't depend on how you topple. So this was introduced by Levin and Joel Perez in 2009, and it was studied in details by Levin, Murugan, Perez, and Ogurkan in 2015. Now, here I didn't tell you what is stability. So I must tell you what is a stable configuration, because the rule has changed. So here comes the third stool, which is another interesting story. What is an odometer? Odometer, those who have drive cars know that this part which keeps track of how much kilometers you have traveled is odometers. So what are the role of odometers? Odometers are things here which will keep track of how much particle, the mass, the particles at a site are emitting. So we'll consider an integer lattice for simplicity here, ZD, which has 2D neighbors. You can think of Z2, which has 4 neighbors. And when I write that 2 points, Y, this is called sim X, I'll mean that X and Y are neighbors in the lattice or in the graph, I can think. So let me denote, let me go into, these are the few slides which will be mathematical. I apologize for this, but anyway, like it's a simple mathematics. So I denote by UMX the total mass emitted by a site X to one of its neighbor before time M. So you look at a point, you look at how much mass it has emitted to one of its neighbors before time M. Now, what you can do is, it's a nice way to look at this. I'll go slowly. So I denote by Laplacian of UMX. This is a definition. I'm summing over all the mass that is coming from the neighbors to me. So UMY, Y is a neighbor of X. So, and minus 2D, I have 2D neighbors. And this is the mass I have given out. Remember, when I give out uniformly to all my neighbors. So if I have 4 neighbors, I'm distributing 24 into 6 equal parts. So it's 4 into 6. So this is the 2D factor which is coming. So Laplacian of that function is the grains received minus the grains given out. So this is the expression which I have. So you think of Laplacian of the odometer. So UM will be called the odometer at time M till time M is the number of grains I have received and minus the grains I have given out. So that is the net thing. Now, suppose you're playing this game of Sandpile and at time M, you want to see what the configuration is. So how will you calculate? So SMX be the configuration at this at time M. So it will be the initial height I had started with. Say it's a random thing. I had started with an initial random thing. And then I calculate the net mass I have. That is the delta of UMX. So this is the configuration at time M. What is the configuration at time M? I had the initial things plus the grains I have received from my neighbors minus the grains I have given out. That is my configuration. Now, if you let M tends to infinity, suppose this makes all the sense. And so you get a nice equation. What is this equation? So you have delta of UX, I call it delta of UX, is equal to S infinity X. This is the final configuration you see, minus S0X. Remember that I'm not claiming here that immediately that S infinity X is some finite quantity. It may be infinite also. U may be infinite also. So if this makes sense, if everything is finite, then the driving equation is this. This is the Sandpile driving equation. Okay. So what is, if now as M tends to infinity, so you have played the game, if the total mass, the net, the total mass that is emitted from one side is finite, after the game has been played, we say the configuration, initial configuration stabilizes. And if this doesn't happen, then it explodes. And again, as I explained you can just think a bit. The same dichotomy happens here also. UX is either finite for all the sites or it is infinite for all the sites. So this is the dichotomy which is kind of carried over in this case also. Now let me give you some results because I have been telling you stories. There are no mathematical results. Mathematics should have some mathematical results, but I'll be, again, not mathematically precise. The game I played over ZD can be played over any graph, any connected graph. Now, okay, you can tell me, does the theory hold for any connected graph? No, not really. When you want to do the mathematics of it, you require something like a ZD or a Bethe lattice kind of structure. And what is it? So these are called vertex transitive graph. I'm not going into the mathematical definition. So there is an automorphism which is acting on each of the vertices and it's preserving that. But suppose you take an infinite vertex transitive infinite. Remember, the infinite is important. The infinite vertex transitive graphs. And you start this divisible Sandpile. So you started with this Gaussian noise. Now the Gaussian noise can have a mean, can have a variance, positive variance. So the Gaussian noise, if the average noise of this Gaussian noise is more than 1. So what does average noise means? That each site, when you started with, the height of the starting height is more than 1. So every site is at an average unstable. Then it's very, very natural to say that the final configuration will be not stabilizing. So the odometer will be infinite. And that's what is happening. It needs a proof, but it can be proved using some easy ergodic arguments that this S does not stabilize. But that's the point is, it's very intuitive. If you start off with heights more than 1, you can think that everything is unstable. And now you're moving this. There is no way that things will stabilize because everybody is more than 1 at an average. So this just explodes. Similarly, if everything is less than 1 at an average, there is a chance that it will stabilize. And that's what is happening, that it stabilizes. Okay, these are in probability statements, these are all happening almost everywhere. There is a nice zero set where these things can fail, but we don't bother about it. What happens if the average noise is 1? This is not intuitively clear. And in fact, it's quite difficult to prove, not very difficult, but it requires quite a technicalities that, so 1 means here that not all of them are 1, some can be less than 1, some can be more than 1, but on average, it's more like 1 exactly. Then it does not stabilize, it explodes again. So there are 3 cases. So you can think that 1 is sort of a critical point which is coming here in this thing. Now this is true for infinite graphs. What happens to finite graphs? Finite graphs, the structure is a bit different. So this is my last episode, which is coming on finite graphs. I'll take a special case called the torus, a discrete torus, and I'll tell you about the conjecture. So this is a discrete torus. You can think of this as a higher dimensional torus, and this is a plot of the Sandpile on the torus. It can form a nice. What is the beauty of the torus is it doesn't have a boundary. You see, it's wrapping around, so it doesn't have a boundary. So that's the beauty here. Now, what happens to stabilization? I can play the same game on torus. I need not be finite or infinite. My graph, my game doesn't depend on whether the graph is finite or infinite. I'll start off with a connected graph V. Say V is a graph, so it has a vertex set, it has an edge set, and it's connected. So you can reach, connected means you can reach any point from any point anywhere. So this is, I would say for the students that this is a nice exercise to think about. You don't require a pen and a pencil to prove this. So for a finite connected graph, the configuration is stable if and only if the total height, the sum of the heights is less than the size of the graph. Note that if the, now what happens is each of these heights, initial heights you see, if they are more than 1, they are unstable. So if each of them are more than 1, it will exceed the size of the graph. And so, and you're not letting anything out. So in physics things, those who know this kind of models, I'm not allowing a sink or something outside which can take in a, so there is someone standing with a bucket catching on things which are falling apart from the graph. That's not the case here. So everything has to be preserved. So there is a conservation of mass when you are taking things from toppling one to another, and it's a finite graph. So this configuration becomes stable if and only if the total sum is less than the size of the graph. It's a simple exercise. You can do it with 3 points and a simple graph like it's a line or something like that, and you can check what happens. So what is a critical case? Critical case is again, just like that the previous case when the mean was 1, here the critical case is when the size is exactly, the total sum of the heights is exactly the size of the total graph. Now the result says that in this case, it's a striking result that the sandpile will, in this critical case, will stabilize, and the final configuration you see will be all ones. You don't see a picture, or you don't see anything. You just see everything is one there. And the odometer, the UI function, the mass emitted, satisfies this equation. Recall my driving equation was delta U is equal to S infinity minus the initial configuration. Now the initial configuration is all ones. The final configuration is all ones. So you see all ones, 1 minus S. Now there's the extra green part. I'm not coming into this. This comes through what is called a least action principle, or from the conservation of mass, that if you want a unique solution of this equation, you have to impose this boundary condition that minimum of U must be 0. Now, there was a conjecture in this paper for a special vertex or a special graph, which is called the torus. What is the torus? You take the grid or take a box of size small n, and you don't keep the boundary. So you just keep that one. So this point is a neighbor of the point below. So again, I'm showing this point is a neighbor of the point below. So you're just wrapping around. So as I said, torus will not have a boundary. So this is a toric structure which is there. So you can think of a person is walking and it coming to the boundary, and then it might topple over, but it goes to the other part of the. So this is what the old people used to think about the flat earth. So people in old times, the earth was flat. So they used to think people might fall and might come from the other side also. So what did they conjecture? They said that if suppose I take this graph and I suppose take the divisible sandpile, and I'm in the critical case where the sum of all heights, initial heights, is ND, and the initial heights might be are random, then they said the odometer, actually the U function, would converge to the biharmonic or a bi-Laplacian Gaussian field. Now, again, you see it's going back to episode 1 that there is a bi-Laplacian. And this is the first conjecture where this appears in form of sandpiles. So we started looking at this conjecture, and so these are some plots of Gaussian fields. So these are sort of the Gaussians I told about. There is a correlation between them, and so these are sort of interfaces which are appearing. So in non-mathematical terms, it's a sort of a mountain landscape. You have random heights everywhere, and these heights are determined by a Gaussian distribution, and there is a correlation between 2 points in the height. So this side is a famous quantity called a harmonic crystal, which is a Gaussian field. It appears in quantum field theory, and this is a simulation we did about the biharmonic Gaussian field. You can see that different regions mean that different parts have different, so they have a same kind of variance fluctuation. That's why these different colors are appearing. There is a qualitative structure. So harmonic crystal, just to tell you, harmonic crystal comes from the Laplacian. The biharmonic comes from the delta 2 I showed in the story of Cladel. Now this is the result in very rough words, that if you look at the odometer, if you scale the torus with n, so you scale the space, the point with n, and the whole height, the odometer, the mass of the odometer with n to the power d minus 4. So there is a phase transition in d is equal to 4. So if you scale this by n to the power d minus 4, it converges to a Gaussian field. I'm not saying how it converges. So this is the rough description of this Gaussian field, that it's a chi-x, it's a function, it's a random function, where for each x, it's a Gaussian. And the correlation, so you think of these are random heights here. So these are 2 points, say these 2 peaks. So the correlation between these 2 peaks are given by the inverse of the biharmonic operator at those 2 points. Now, Okay, this is hard to make it precise in general talk, but this is what it is. Now, coming to the story, how to prove this, firstly, you have to make it rigorous. We go back to the old theory of waves, which was described by Fourier transforms by Joseph. So this side is Joseph Fourier, and this is the Sobolev. So Sobolev was another brilliant mathematician. It's a completely functionality proof. So you use a lot of function analysis, you study the wave equations and get to the solution. And so that's the method. Just I say two names, Fourier transforms and Sobolev spaces. These are the two methods to prove this result. So this is just to mention, this is a joint work with two of my collaborators, Alessandro Cipriani and Violetta Rudzel. Okay, so here we are almost at the end. The beginning is the end and the end is the beginning. So this is in Latin called the sic mundus creatus est. So are we ending or are we beginning? It's not very clear here because you see this operator, which was shown in season or episode 1, comes back here again, but it doesn't link much. So here are the questions which arise, issues which arise in season 1 or season, so these might be sorted out in season 2 at some point. That what does the scaling limit mean? I give you a result. I didn't tell you how it converges. The inverse of the biharmonic operator I wrote, that doesn't make any sense. That's you can throw that off. That's rubbish. That doesn't make sense. That is not a mathematically correct. The inverse doesn't even exist in that. So what does it mean here? What is the relation I showed between the fractals and the biharmonic Gaussian field? This is not yet known. What about, I did it for a torus. We did it for a torus. What about other graphs, other networks? The driving equation remains the same for other vertex transitive graphs, but you cannot say about scaling limits much. And where does the forest come in? Random forest. Just let me tell you the random forest. So you take a forest. What is a forest? Forest is a collection of trees. It's trees, what do I mean? That these are graphs which doesn't have loops in them. So you take a collection of these trees. Say, suppose you have a infinite collection of trees. It's a huge forest. Now you suppose you play a game now on this forest. You go to every tree, you toss a coin, a fair coin. If it lands head, you put 1 on the tree, you mark it as 1. If it falls tail, you mark it as 0. So think of, you have went to or a walk on a big forest, you have marked each tree 0s and 1s. Now, so you get a picture of 0 and 1, 0 and 1s. Now, if you magnify this picture or dilate this picture, the claim is you will get a gain to the Gaussian, biharmonic Gaussian field. That can be proved. That there is a proof for that. Next is, if you look at Dhar's initial works, Dhar and Majumdar, they showed that the Abelian Sandpile can be driven by a Markov chain. So whatever it is, it's a stochastic process, it's a Markov chain. And the recurrent configurations of this Markov chain, so the configurations you see again and again, the pictures you see again and again while playing this Sandpile game can be related directly with which is called a burning bijection between the uniform spanning forest. So now one has to make the link, which is not there yet. So maybe next time when we get chance in season 2, we'll see the thing. Finally, this is a big credit to Lionel Levin, who has done tremendous work in Sandpile. And this is the maestro, Professor Deepak Dhar, the physicist who described the Abelian Sandpile. And these are my collaborators, Alessandra and Violetta. And this is a conference in Bangalore where all the Sandpile groups gathered together. And this is a group which I show my gratitude today, because this is a group of physics chemistry and mathematics in St. Xavier's in 2003. And as you can see, all the mathematicians are interlinked with the physics and the chemistry. And this is how all my interest in the different areas of subject came in. And that's it. I would like to thank here. And I might stop sharing and look for questions. Thanks a lot.
Rakshi Biswas from third year mathematics department. So firstly, I'd like to thank you for that engaging session. It was extremely enlightening and you have given us a lot to think of. So now I'd like to start off with the questions. So the first question is from Professor Ashok Nath. So
Okay.
you've mentioned fractal structures. So could you
Yeah.
please explain how to get these fractal structures?
Now so these fractal structures, which was shown in the Sandpiles, the stable configurations, they don't. So I just said fractal because what you can do is you can zoom in the picture. The picture I showed you was a zoomed out picture. If you zoom in, you will slowly see a similar structure inside that. And if you zoom in more, you will see inside again there is the same structure. So there is a self-similar nature which kind of gives this fractal thing. So there is no description. The interesting part is this is not known. As I said, this is not known what are these fractal structures are actually, because it's a mixture of Sierpinski gasket, it's a mixture of Cantor set, it's a mixture of different kind of things. It's a very, very hard question. It's one of the most difficult conjectures to prove at this point. That's my answer.
Thank you. So from the second episode, so do you feel that the Sandpile creation is not deterministic, or is it non-deterministic or a chaotic process? So this question is also from Professor Ashok Nath.
It's definitely, see, the Abelian Sandpile is a deterministic dynamics, as you see, because what I did was I had an initial height configuration. I added lots of sand in the center, and then it was the toppling procedure which gave this thing. But there is a randomness here. What is, if you call configuration at time n as some kind of, say, xn, then you can show that this is a Markov chain actually. So Markov chain is what? A Markov chain is a process which, when you condition, if I give you the information up to time n, you will only depend on the n minus 1th step or the nth step. So the n plus 1th step will depend only on the nth step and not on the whole previous generation. So these kind of Markov chains, and the pictures you see are sort of the states which this Markov chains visit on a configuration space. So there is definitely a randomness here. So this is a stationary state you see in the thing, but it's not coming from the dynamics. I'm saying the dynamics is deterministic in that sense. So, and what is chaos? I don't know. Like, chaos is very difficult to describe in mathematical terms, but this is what I would say. It's a deterministic one, and the divisible one, I would say, is the random one.
Thank you, sir. So from the second episode, Professor Diptiman Shah had a question. So what do you mean by self-organized sandpile? And is it a fractal?
No, self-organized sandpile is not. The word is, I think, more precisely, maybe I have said it wrongly. So it's called the self-organized criticality. Self-organized criticality is, the sandpile is a system. So it's a mathematical system. Self-organized criticality is a process in which the sandpile moves and comes to a stable thing. Now, why do we say criticality? Because in physics, what happens in the equilibrium state, there are many properties of a system which can be found out. For example, if I look at the heights of the variables, or if I look at these avalanches, the huge jumps which at each stage the sands make, they have power law decay. This is what is predicted, and some are proved also. This is what is predicted. So these are at criticality. So this is the behavior which is expected from the system. That's why it calls that if you give a slight push, so it's like standing on a hill, and if you push someone, he will keep on rolling and rolling on itself. So there might be some frictions or something, And so the system will come to an end slowly. So this is what is called self-organized, because things are driven on itself once you give a little push to it.
Okay, sir. Thank you. Sir, from episode 3, Nilavya Mehta wanted to know that if S infinity is divergent, but not infinity, does the dichotomy hold for every infinite graph as well?
Yeah. The dichotomy definitely, because my description is for the infinite graph ZD. The dichotomy, it's a very simple exercise. Just go through it again. So it's again that if there is a site which is stopping at some point, then there are neighbors who haven't toppled yet. So it will give back itself some mass, and it will start toppling again. So that's the dynamics, or the dichotomy will be again true, even if the graph is infinite. And the question which was that the S infinity might be infinite, it can be infinity also. So it can be infinite mass. So it's not that it is finite. That's what I said, that the odometers, when it is finite, then the S infinity is finite, and you see a configuration, the final configuration you see has height less than 1.
Okay, sir. Thank you. So the last question, so from
Okay.
Shorojyoti Maiti, is there any abelian group structure in the abelian sandpile game?
Yeah, that's a very good question. There is definitely a group structure in it. I'll not go into the details, but definitely, if you look at Dhar's 1991 paper, there is, so these topplings, each toppling gives rise to a nice toppling operator, and there is a group structure between them. There is a very nice, so these are called the Sandpile groups in it. And it's an interesting question to identify these groups, actually, Sandpile groups. I'm not going to the algebraic part in that, but definitely this is a very good question, and there is a link to it. Okay.
Thank you so much. So now I'll give the control over to Shajuju. Thank you.
Thank you, Mayurakshi, for such an interesting question and answer session. I would now request Professor Deeptiman Shaha to deliver the vote of thanks for today's webinar. Over to you, sir.
Thank you. Thank you, Shajidjo. I feel proud to say that Rajat means Dr. Rajat Subhra Hazra was my student. Thank you, Rajat, for giving this wonderful lecture. I like to thank our rector, Reverend Father Jayaraj Velusamy, our principal, Reverend Father Dr. Dominic Savio, Vice Principal, Arts and Science, Professor Bertram da Silva, Dean of Science, Dr. Tapati Dotto, Dean of Arts, Dr. Orgho Banerjee, Member Secretary, Academic Council, Dr. Ayan Chando, and Dr. Parthopratim Ghosh, Coordinator, IQAC, for their support and cooperation, without which this program cannot be successful. I'd like to thank specially our enthusiastic head of the department, Professor Sucharita Roy, and her team to take trouble for organizing this seminar. I should not forget to give thanks to Computer Science Department, especially to Romit Bid and Jayati Ghosh Dostidar and Shalav Agarwal for providing their technical support. Finally, to all the faculty of the department and the college and students of the mathematics department, especially Shajujjo and Mayurakshi, thank you all of you for your cooperation and presence. Lastly, I thank audience to join here. I know that there are some professors in the audience who teaches Rajat, particularly Anando, I think present now. Thanks to all.
You. Thank you.
Thanks to all of you. Finally, again, Dr. Hazra, congratulations for your Vatnagar Award, and thank you to join this webinar and be among with us. Thank you, everybody.
Thank you, sir. Thank you.
Before we end the webinar, there are a few key announcements that I have to give you. So we will post the feedback link in the YouTube chat box, and you can go and fill up the form from there to download your certificates. Your certificates will be given out in a few days' time, right? And the forms will be accepting responses for the next hour or so. So yeah, that's it from us. Have a very good puja ahead. Thank you everyone for joining here today. Wish you and your family a safe and prosperous life ahead. Thank you.